Since 1916, we physicists have been waiting for this moment. Black holes may be one of the most fascinating and mysterious phenomena in the universe. Despite their immense power, they are almost entirely invisible. Until the last few decades, we knew almost nothing about these massive black holes, which can have masses millions of times that of the Sun. However, thanks to research, we have started to learn more about these colossal objects. Michio Kaku has announced new information that finally allows us to peek inside a black hole, shedding light on details the scientific community may have overlooked. Join us as we delve into the depths of black holes and discover what lies within them. Before we delve into Michio Kaku's findings, let's share some information for those who do not fully understand what black holes are. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the concept of a black hole was entirely theoretical, and it took until the 1960s for the scientific community to find evidence that black holes actually existed. During this period, while studying the constellation Cygnus, they discovered a bright blue star emitting X-rays. This star was orbiting around a massive dark object. Further research showed that the X-rays were not only moving, but also being drawn into this dark object in their orbits, giving rise to the term black hole. This discovery provided concrete evidence that black holes indeed existed, and that Albert Einstein's predictions were accurate. This incredible discovery revealed the existence of these mysterious entities in space, emphasizing the need for more information about them. As a result, researchers around the world accelerated their efforts. This black hole was named Cygnus X1 and was found in the constellation Cygnus. Located about 6,000 light-years from Earth, it was a significant discovery. This object is about 14 times more luminous than the Sun and incredibly dense, which gives it a powerful gravitational pull. Its gravitational force is so strong that even light cannot escape from it. This is why the term black hole is both fascinating and terrifying. It describes a region in space where the gravitational pull is so powerful that nothing, not even light, can escape. Therefore, any object that gets too close to a black hole never returns. This dangerous characteristic makes it even more necessary to learn more about black holes. The discovery of Cygnus X1 led scientists to search for other black holes. They found that there could be over 100 million black holes in the Milky Way. But because they are incredibly difficult to detect, we do not have an exact number. Still, it is believed that there are several million black holes in our galaxy. The black holes in the Milky Way make it even more important to study them. The primary concern with black holes has always been gravity. The gravity is so intense that anything that enters gets compressed astronomically and ultimately becomes a singularity. Black holes act like cosmic vacuum cleaners, pulling everything into them. One of the most frightening aspects of research on black holes is that if someone were to fall into one, they would be stretched and thinned out into a single line. This process happens gradually, and the person would die before reaching this final form. Therefore, it is clear that no one should approach a black hole. But are we really in danger? The closest black hole to Earth is about 1,500 light-years away. In 2021, when scientists released the first clear photo of the M87 black hole, this discovery still raised many questions and concerns. This black hole was photographed over several nights. Researchers gathered more evidence with each photo and combined these photos to create an image that filled in all the gaps. Thus, they understood that a black hole has 3 layers. This shows that, contrary to what many people believe, the phenomenon does not have a simple structure. To reach the innermost part of a black hole, one must pass through the first 2 layers. The first layer is called the event horizon. This layer is the point of no return. Once you pass the event horizon, there is no going back, and you are inevitably pulled into the black hole. From there, the situation worsens. The second layer is the photon sphere, where light orbits are located. Any light entering the black hole is trapped in this region and cannot escape the gravitational pull of the black hole. Finally, we reach the third layer, the singularity. This is where everything that enters the black hole is compressed astronomically. The singularity is a point where the known laws of physics break down, and we cannot predict what will happen in spacetime. The density is infinite, and it is where our understanding of physics ends. What makes all this even more complex is that while every black hole you study tends to follow the same three-layer structure, they can actually be extremely different. The way black holes function can vary greatly from one to another. In other cases, we could simply go back and examine the problem in detail with telescopes. However, this is not really possible with black holes. Scientists can only study them indirectly by observing the radiation they emit. Due to the gas and dust surrounding black holes, it is impossible to send a spacecraft like Voyager into a black hole because anything that enters the event horizon is pulled into the singularity and compressed into an infinitely small point. So, you can't waste billions of dollars completely, because when the probe gets close enough, it will be crushed into nothingness. Due to this major issue, scientists have no choice but to study these objects in 2 dimensions. These phenomena, which are actually 3-dimensional, make things even more difficult. There are 2 major problems. Every black hole is unique, and the laws of physics as we know them break down when trying to explore their interiors. This means traditional scientific methods do not apply in these cases. However, this does not mean researchers are not working on black holes. There are many different theories and explanations about black holes, each making the subject even more fascinating. One of the most intriguing theories about the formation of black holes is that they form from collapsed stars. When a star exhausts all its fuel, it can no longer generate enough energy to counteract the gravitational force pulling it inward, and as a result, the star begins to collapse. It shrinks and condenses into itself. If the star is large enough, this process can continue until a singularity forms. To deeply understand the nature of black holes, NASA scientists turned their attention to the core of the M87 galaxy. Astronomers observed a powerful vortex of superhot hydrogen gas spinning at an astonishing speed of 2.2 million miles per hour. The force of this spinning gas disk should have caused the gas to be violently expelled in all directions. But scientists saw that this was not the case. To explain this, there had to be an enormous mass concentrated at the center of the galaxy. This colossal object, weighing between 2 to 3 billion times the mass of the Sun, could only be a black hole. However, in 1963, this was not the only theory regarding the rotation of black holes. New Zealand mathematician Roy Kerr used Einstein's gravitational equations to provide the best description of a rotating black hole. Kerr showed that a rotating black hole would collapse not into a point, but into a ring of fire or a thin disk. The black hole was spinning so fast that centrifugal forces prevented it from collapsing. This spinning disk of matter, called the ergosphere, is the region surrounding the black hole where the laws of physics start to break down. The most interesting feature of Kerr's solution was the prediction of the existence of a wormhole, also known as an Einstein-Rosen bridge. This is a theoretical space-time passage that connects 2 separate regions of the universe or 2 parallel universes. The idea here is that if a person were to fall into a black hole instead of being crushed into oblivion, they could be pulled through the ring of fire into a tunnel and ejected out of a white hole in a parallel universe. To understand how this works, we need to look at the concept of space-time in Einstein's theory. Space and time are not separate entities, but form a 4-dimensional fabric that is interconnected. Mass warps this fabric, creating a gravitational field that causes other objects to move towards it. Now, imagine marking 2 points on a piece of paper that represents space-time and drawing a line between them. This represents how objects move through space-time. But what if you could fold the paper and create a shortcut between these 2 points? This is the basic idea of a wormhole. It means creating a shortcut in space. Wormholes are gateways that connect two distant points instantaneously. This is not just science fiction. It is a prediction of general relativity. However, no one has directly observed a wormhole because they are inherently unstable and collapse almost instantly. The existence of the Einstein-Rosen bridge implies that black holes are not just cosmic vacuum cleaners, but also gateways to other regions of space-time. So, can we travel through space and time using a wormhole? Unfortunately, the answer is probably no. Even if we could stabilize a wormhole, it is unlikely that we could use it to travel faster than light. Einstein's special theory of relativity predicts that the speed of light is the absolute limit for how fast anything can travel through space-time. However, the theory that wormholes and black holes could be pathways to other regions of the universe, and even different times, has been a source of fascination and speculation among physicists for decades. The idea of shortcuts through the fabric of space-time and even time travel could be revolutionary. One of the most intriguing concepts in this field is the Kerr wormhole, named after mathematician Roy Kerr, who described it using Einstein's gravitational equations. A wormhole is a hypothetical tunnel that can connect two different universes or two different times within the same universe through space-time. The Kerr wormhole is often visualized as a ring-shaped portal, much like Alice passing through the looking glass in Alice in Wonderland, where she enters a world where animals speak in riddles and logic is not always consistent. Passing through the Kerr ring could take a traveler to another universe or time. The laws of physics might be very different, but the destination could be normal. The idea of wormholes being a means for interstellar travel or time travel is certainly exciting. However, it is also a controversial topic. Debates among physicists suggest that the intense radiation and subatomic forces surrounding the entrances to wormholes, especially Kerr wormholes, might make the passage unstable or impossible. Critics argue that, while Einstein's gravitational equations are used to describe wormholes and black holes, understanding the true nature of these phenomena requires a new theory that can combine the laws of gravity with the quantum theory of radiation. This theory is called the theory of everything, a single theory that can unify both Einstein's theory of gravity and quantum theory. Renowned theoretical physicist Michio Kaku has been working on the theory of everything for decades, and there are many different versions of what this theory might be. The most promising theory is the superstring theory. Superstring theory combines gravity with the theory of radiation. It suggests that subatomic particles are actually tiny vibrating strings, and just as different musical notes correspond to different vibrations, the universe is a symphony of these strings. Just as the strings of a violin correspond to different particles in nature, the different vibrations of a superstring correspond to different particles. One of the fascinating aspects of superstring theory is that as a string moves through time, it warps the surrounding fabric of space, producing black holes, wormholes, and other exotic solutions. Superstring theory not only unifies Einstein's theory of gravity with quantum theory, but also explains many of the mysterious events we observe in the universe. It may seem complex at first, but it actually makes sense. Superstring theory requires 10 dimensions of space-time in which the strings can vibrate. This is quite different from the three-dimensional space and one-dimensional time dimension we experience in our daily lives. While it is difficult to imagine what these extra dimensions might look like, physicists have developed some conceptual models that can help us understand. These models are akin to imagining a pond inhabited by fish that are only aware of the dimensions of length and width. Fish cannot understand the concept of height and cannot imagine what it is like to live in a three-dimensional world. But if rain falls on the pond and creates ripples, the fish can experience the effects of the third dimension, even if they cannot directly see it. Similarly, physicists believe that we cannot directly see the extra dimensions of space-time, but we can observe their effects on us. The vibrations of the strings in superstring theory can produce energy waves that move through the extra dimensions of space-time. These waves can manifest as particles with different properties such as mass and charge. Thus, superstring theory can potentially explain all the particles and forces we observe in the universe, including gravity. However, there is a problem. The extra dimensions of space-time required by superstring theory are so small that we cannot directly examine them. The most sensitive measurements we can make in our laboratories only use the 4 dimensions of space-time, which are length, width, depth, and time. So, how can we know that extra dimensions exist? One possibility is that these extra dimensions are tightly curled up, making them invisible to us. An ant walking on the surface of a piece of paper might not notice that the paper is curled. The extra dimensions of space-time in superstring theory might be similarly invisible to us, curled up in small loops or spirals. Another possibility is that the extra dimensions were more prominent at the beginning of the universe during the Big Bang. According to some versions of superstring theory, the universe started as a 10-dimensional space-time. As the universe expanded and cooled, the extra dimensions began to curl up and collapse, leaving the 4 dimensions we observe today. If this scenario is correct, we could detect traces of the extra dimensions around us. The mathematics involved in superstring theory is incredibly complex and has opened new areas of mathematics that were previously undiscovered. However, solving the quantum black hole problem has proven difficult as many physicists try to tackle this issue. Edward Witten from the Institute for Advanced Study in Princeton described superstring theory as 21 century physics that fell into the 20th century. Last year, several groups of physicists independently announced a significant breakthrough, finding that superstring theory could completely solve the quantum black hole problem, but only in 2 dimensions, not 10. Many physicists believe that given these equations are well defined, it is only a matter of time before someone solves this problem, but it is still very early. While it is not yet possible to buy tickets for intergalactic travel or time travel expeditions, one thing that is clear when it comes to black holes is that there are many questions and even more solutions to these problems. Michio Kaku explained that despite all the crazy theories, knowing what the truth is, the infinite answer problem is not unique to string theory. In fact, many major theories have an infinite number of solutions. For example, Newton's laws can predict the motion of various objects, from rocks to rocket ships. However, before predicting their motion, you need to specify what you are trying to explain. These are called initial conditions. In string theory, similarly, you need to specify what you are defining in the theory. However, unlike other theories, the initial conditions in string theory are the Big Bang itself. This means you need to define the conditions at the moment of the Big Bang, which is currently unknown. There are a few ways to approach this problem. One possibility is to find the initial conditions experimentally, describe the moment of the Big Bang, and then allow string theory to explain how the universe evolved from there. String theory already has solutions that explain the evolution of our universe since the Big Bang, based on some reasonable assumptions about its nature. This is a significant achievement. A more ambitious approach is to demand that string theory selects its own initial conditions. This is a bit more complicated and less likely. However, it significantly narrows things down. Here, Michio Kaku takes a different perspective. Perhaps the Big Bang wasn't that big after all. After all, he says it didn't produce as loud a sound as many might expect from an explosion. The Big Bang theory doesn't provide an explanation for this. It only states that the event occurred without explaining what caused it or how it happened. The fact is, we need a theory that can explain what happened before the Big Bang. This is where string theory comes into play. According to this theory, our universe could have formed. Our universe might have emerged from the collision of 2 separate universes, or from another universe, much like a mother giving birth to a baby. This connection between universes is called a wormhole and can be thought of as a tube connecting 2 bubbles. We may have discovered evidence of this before. The umbilical cord connecting our universe to another could be inside a black hole, but we don't know for sure. This is because we exist in 4 dimensions and cannot see beyond that. We might actually be living inside a black hole, and the black holes we study could be wormholes leading to these other dimensions. Do you think there could be some truth to this theory?